hopefully you may have seen in the materials that were sent over, what we've announced just recently is Clarity, which is our perception platform for automotive. And we think it really fills a missing gap in the assisted driving and autonomous driving systems that are being built and launched into the market today. And specifically, we think the gap that exists is that these systems for perception that allow the vehicles to see the world around them, they don't see far enough and they don't see in enough detail. And Clarity attempts to solve this problem by using a camera-based system rather than LiDAR or radar, which, as you know, are active systems that emit, in the case of LiDAR, lasers, and in the case of radars, radio waves, to try to bounce off of objects and come back and give some sense of distance of objects that can be seen. So we're doing the same thing, but doing it with cameras and using cameras a bit differently than current players in the market are today. So let me just share my screen. So I just wanted to give you a visual reference. This is a test vehicle of ours that we use for designing and developing our product. And what you're seeing here is a number of cameras labeled A1 through A4. This is just one example of a reference implementation. The middle top A1 is we call the reference camera. I'm going to be showing you some footage as if you're viewing the world from this camera. But we're simultaneously running all these cameras, and in real time at 30 frames a second, we're using something that is basically the same principle by which we as humans see depth, which is called parallax or stereo vision. So when you have multiple cameras or two eyes, you're able to, through a process called parallax, determine depth of things in the world. And of course, with computers and cameras, you can get much more precise depth and a much greater range. And so this, again, is a test rig. Obviously, if this were a production vehicle, you would have cameras in the A-pillars and behind the windscreen, behind the rear view mirror, and so forth. But since we reconfigure this from time to time, it stays on the top of the vehicle. And to give you a quick comparison of what we see versus traditional systems, we're headquartered in Redwood City in the Bay Area of California. And what you're looking at here is just the cameras looking at a street in Redwood City. We often ride with a LiDAR on the vehicle. And this is a LiDAR return, which I'm sure you're familiar with. Not a state-of-the-art LiDAR, certainly, but not a cheap one either, and 32-channel LiDAR. And like by industry convention, each dot is a return. So every one of these is about 75,000 returns or data points on this slide. And the red, orange, yellow, green, blue, indigo, out to violet is representation in color of how far the distance is. We use the same color scheme. And of course, what you can tell right away is the richness of the depth data provided by a camera-based system using this stereo optic approach, or multi-stereo as we call it, is far greater, whereas this is about 75,000 points. This is about 1.8 million points of data. And you can see right away that when you have this much data, you're actually, even as human eyes can tell, this is a vehicle, this is a street lamp with some street signs. And the way people running LiDARs have to do this is they will fuse this camera. They have cameras as well, monocular or single cameras. They'll fuse this camera with the LiDAR so that they know, for example, this row of points is reflecting off of the back of what now is known to be this SUV in the scene. So, so a couple of key differences right out of the gate in how we do it. And also then the LiDAR and camera only folks will be using artificial intelligence or machine learning to understand what things are in the scene. So with that kind of baseline, let's just jump into a demo. What I've got here is, this is San Francisco, California street, a challenging area to do perception given the hills and terrain. And I'm going to run this at 15 frames a second just because it's less clunky on Zoom if I do that. And what you'll see as I start this video is this is the reference camera view, as I said, A1. You see a motorcyclist come into the frame. And over here, I've got vehicle info, the GPS coordinates, the compass heading or bearing, IMU information on the pitch, roll, and yaw. The lux meter, this is just telling us how bright it is, very bright day at 9,000 lux. And again, all 4 cameras are running and processing the depth, but I'm showing you just kind of a human viewable video stream out of one camera. So what I'd like to do now, though, to show you, where the magic is in this type of perception system, is go into our single frame analyzer so I can look at a detailed view of the frame. And now you'll see what the computer sees processing all the cameras together in a single view. So it's enhanced with color. The colors are enhanced to make it more human viewable. And I can always look at it from this pixel depth, as we call it, seeing a visual of the depth. But we also have this construct called pixel cloud, which is like a point cloud a LiDAR puts out, but with much more information. And this is where things really start to get interesting. So now it still looks like a photograph to you or a regular picture, but it's actually not. What you're looking at is that in this frame, for every pixel in this view, we get the color information, but we also get the exact depth information. And you'll see up here on the left, where I'm waving the cursor, wherever I put my cursor, it'll tell you how many meters in front of the van the object is. So now I'll zoom in a little bit to the motorcyclist here, and you'll see what I mean. As I rotate around, it starts to pixelate, and you see the exact 3D structure of this motorcyclist is maintained in perfect 3D form. And if I come back over and focus on how far he is away, I see that the tire looks to be about 28.56 meters away. The backpack's 29.1 meters, the helmet 29.4. So you're getting this very precise measurement per pixel. And this is what I mean in terms of the difference of various systems. So a typical camera-based or camera plus LiDAR-based system has no knowledge of 3D structure. And in fact, what happens is, if I pop back out, whether you're Tesla using cameras only or you're Waymo using a camera plus a LiDAR, the first thing you're doing is through your cameras, you're seeing this picture, and you run it through your neural network, and your AI tells you this is a motorcyclist. Okay, so if it's a motorcyclist, then in the case of a Tesla, or a Mobileye, the answer would be, well, since I know this is a motorcycle, I can use scale. How many pixels is this taking up on the image sensor? And that scale will tell me it's 29 meters away. And of course, that's where failure cases happen, as you guys are well aware. This works very well if you've had millions and millions of examples of data to train your system on. But if you see something you're not expecting, such as a semi-truck going across the highway perpendicular to it, that's a long tail situation and a tragic accident could occur. And with LiDAR-based systems, remember that they can put this through a neural network and say, okay, it's a motorcyclist, but they still have no idea of 3D structure. They just have a point off the back of the motorcycle to give it a distance. And the problem that generates is like this. Let me go back over here if I move mine. Is this kind of dilemma. I don't know if you happen to catch this from the Electric Future Handle Twitter account, but this was this is down in Australia, where the person took a screenshot of his Tesla monitor and talked about the car braking, because with a Tesla system or even a LiDAR and camera, you can't tell the difference between the drawing of a man and an actual man, right? So of course here the Tesla thinks it's seeing an actual human being who's much closer to the Tesla than the bus and much bigger, because again, it's going by scale. The humans aren't this big, so if I think that's a human, it's got to be closer, and that's kind of a classic mistake today's systems make because they don't have 3D structure. So, and even in this frame, going back to the idea of misidentifying things, if you want to predict something's a pedestrian and might the pedestrian step in the road and be a hazard, we even noticed in this frame, there's something that could be a problem for AI. When I zoom to this pedestrian, we'll see she's holding something like a flip chart or an easel here, and that might not be immediately recognized by a neural network, because if you haven't had enough points of data to train on this, it could be mistaken itself for a street sign, because that's a common thing. Something vertical with a rectangular sign on it would be quite common. And then sort of the last thing to kind of point out again is the range. You know, if I go back and look at this scene and we go down to this building's a little over 1,000 meters away from the vehicle. Very key missing piece in autonomous today, certainly for L4 trucking, you know, the semi trucks of 175, 180 meters to come to a stop. If the truck's only got half a load, you can double that distance. And so the best LiDARs today can see about 250 meters of distance. So if you need 350 meters to stop, that's kind of a problem.
Just a little background on who you guys are. You're not a new company. You guys started with cameras 5 or so years ago.
That's right. We started in 2014. That's right.
This is not necessarily new technology for you guys. You're just implementing it into the autonomous sector, correct?
That's right. Yes, correct.
Without a neural net or AI training, how would you distinguish between road lines and train your vehicles for different areas like San Francisco or construction zones?
Great question. Great question. So, so typically we are, we're another sensor, if you can think of us that way, like a LiDAR, like a radar. And as we're working with partners today, we work with people. We haven't publicly announced any partnerships, but we are working with traditional auto OEMs. We're working with tier one suppliers. We're working with full stack autonomous companies. And our model would be to be like a radar or a LiDAR, so that all these systems will have their own neural nets and perception platforms. So what we hand off just like a LiDAR would hand off a point cloud to the neural network, we would hand off our pixel cloud, even in a PCD format if that was requested. So the neural network can run as usual. So the benefit really here is yes, you definitely want the neural network to see and understand things like lane markings and roadsides, and it is important to know that this is a motorcyclist. But when these neural networks hit edge cases and fail, that's where we want to be a redundancy and be able to say, well, look, I may not know this is identify this as a pedestrian, a person, but I know that there's a 3D structure in that spot moving at a certain rate, and I therefore want to avoid it at all costs. So that's the added layer of redundancy, if you will, that we provide.
Why limit yourself to just cameras using depth perception instead of adding radar as well, or another LiDAR system on top of it for a more perfected solution?
I think that's wise to do so, particularly as we get to L4 and L5 solutions, right? I think these all, a robust sensor suite that includes LiDAR, radar, light, clarity, and ultrasonic is really important for redundancy and fault tolerance. I think, we do sell our solution as well for those kind of safety and comfort and convenience use cases for L2, L3. So adaptive suspension control or lane centering or things like this. And I think maybe when you're looking at cost benefit, for systems like that, you may not be looking for all the fault tolerance you need in an L4 or L5 solution.
So your solution's sort of modular. You could kind of just add more cameras, add radar to achieve a higher level of autonomy.
Absolutely. Yeah.
How much more would need to be added for level 4 or 5?
So for true level 5 autonomy, we would envision, a light clarity solution that's 360 degrees around the vehicle. LiDAR covering the same range, and then radar probably in the forward-facing direction. And the benefits are that beyond the LiDAR range of 250 meters, you now have light to give you out to 1,000 meters of perception. So this is very useful even in non-trucking applications for things like route planning, being able to see an issue going on the freeway, whether it's a construction zone or an accident, and exit the highway and reroute the vehicle, whether it is stopping distances for larger vehicles. And inside of 250 meters, you would get the fault tolerance and redundance of having both the light, clarity, and the LiDAR solution.
And with just cameras, I have a Tesla right now, and I drive on autopilot, and I see a big issue with low visibility, rain, snow. How would this solve those issues?
So great question, and a number of ways. I think we've got, not on this demo I have today, but we can send you, if you're interested in, for the print side of your business, the some great low light scenes from this app that I'm showing you called In Depth, that show we work really well with conventional headlights under even 1 lux of light, and that's just by the non-custom stock headlights on the Chrysler Pacifica you saw. So, and we achieved that in a couple of ways. One, we were able to reduce or remove the IR cut filters from the camera. So we're now seeing in the IR non-visible spectrum of light. That makes a big difference. We can set other cameras at different exposures. So, in other words, if headlights are coming toward you and you've got a long exposure, then you're going to overexpose that. But you can have other cameras that are a very short exposure to create a higher dynamic range. So we do this as well for the inclement weather kind of conditions, and for the true kind of hard use cases. The hardest is probably very heavy fog. We are on the roadmap. We don't have that solved yet, but we think the approach there is going to be additional IR cameras getting into shortwave IR.
Do you guys see yourself as a software or a hardware company?
Yes, the answer is both. So the solution we sell is our computational imaging algorithms running on our ASIC. So we have a piece of silicon, a chip, that we sell to the OEM or tier 1 as part of the solution. So our operating model is we work with the tier 1s and the OEMs for the autonomous system they're building to integrate our perception piece of the platform and sell them the software and the ASIC. So the chip is part of the solution. And in the case of people that do their own silicon, we also have a soft IP, so that instead of selling a physical piece of silicon, we can just provide the soft core, or the so-called RTL, that the manufacturer incorporates on their own chip.
You mentioned that a market-ready product would have cameras implemented into the A pillar, B pillar, the car itself, not stacked on top.
Yeah, that's correct. We do a number of meetings with the design groups at the OEMs, and sharing our tolerances, for position, for vibration, and so on and so forth. And those have been the positions suggested that people are very comfortable can meet all the specifications, as well as the bumpers. So all the pillars, the ABC pillars, the front and back bumpers, all seem to be very ideal candidates. And the cameras you saw in the demo were rather large industrial housings that we built up for robustness, since we're putting them there. But they're much smaller for in production cameras that could fit in those other places.
Would a consumer be able to purchase your product as an attachment, a third-party sale, or are you strictly looking for an OEM partnership?
Yeah, we're strictly selling through the channel or directly to the OEM. We actually don't have aftermarket product, nor do we have plans for an aftermarket product.
Where do you see the cost of something like this being compared to like Tesla's autopilots now, $10,000 and continuously increasing?
Yeah, so our solution will range based on the use case, like we talked about, whether it's L2, L3 kind of applications or more autonomous L4, L5. For a forward-facing 3-camera solution, we anticipate the price to the OEM will be around $150. Now, going to complete 360 coverage of the vehicle for a full autonomous solution will be closer to $1,000.
Would something like this be connected through over-the-air updates to continuously improve?
Yeah, absolutely. Yeah, we would absolutely. The idea would be to update this as enhancements are developed in a real-time fashion.
This might seem redundant, but what happens if like mud covers a camera lens? It's a big issue I see with Tesla's solution of having strictly only cameras.
Right, right. So a couple of things. We're working with a number of the manufacturers on, the lens or the surface cleaning technologies that are part of this. So you do have the notion of synchronized cleaning or wiping of the surfaces to make sure that debris is removed as the first step. There are also things we can do in signal processing to remove these particles. So when particles, hit the lens and are detected by the imaging sensor, if it's not full on mud, it's just heavy dust, or you're in a dust storm, we can actually, with signal processing, remove these particles from appearing in the image that has to be calculated to determine the depth. And then finally, if there's just a catastrophic failure, mud and the cleaning mechanism has failed, then you would get a system fault and a disengagement.
Do you see this technology being able to do something like Robo Taxis? Or because of
Oh,
that low chance of having a disengagement, it's not really feasible?
no, I think this is certainly suitable for robo taxis. I mean, we have a number of other things that we do with OEMs. So, for example, we can build redundancy for our partners into the system itself, right? So again, if you think of a full robo taxi, you're probably talking about anywhere from 10 to 14 cameras around the vehicle, depending on what sorts of redundancies you want to build in. They're likely, with a multi-sensor solution, you'll be seeing other redundancies in the form of LiDAR and ultrasonic, for example. And robotaxis are going to tend to be a lower speed as well. So, with our partners, we're designing, in every direction, can I survive, X cameras in that direction, covering that field of view failing. And again, that's just a cost benefit trade-off depending on how much redundancy the customer wants built into the system.
Okay, we've seen your testing vehicles, but have you guys actively been testing any autonomy features, or are you just gathering data on the cameras itself?
We're just gathering data on the cameras itself. We're working with our partners. As I mentioned, we're not announced, but we have a number who have taken an evaluation license of our technology, and through the partners, we'll be testing those various features of autonomous.
Okay, thank you. Dennis, do you have anything?
Yeah, I have a couple questions. Hi, Dave.
Hi.
So on your website, it states that the minimum requirement for your system to work is 2 cameras and the accelerator. Could you touch upon what type of features you can expect with the bare minimum requirements for the system?
Sure. So the bare minimum requirements really define a system that will serve you for these L2, L3 use cases we're talking about. So something where your range is a more narrow window. And when I say narrow window, I mean, maybe 0 to 250 or 300 meters instead of to 1,000 meters. Or alternatively, depending on the cameras you pick, you may want to really have good depth measurement from starting at 100 meters from the vehicle to 300 meters or something like that. So it gives you a narrower range of depth you can cover, is the primary trade-off for the lower cost solution. But certainly very good for things like adaptive cruise control, forward collision avoidance, adaptive suspension, things where you need to see 150, 200 meters out to see where there's a pothole or a problem with the road, lane centering as well, things like that.
So correct me if I'm wrong, but by my understanding, this system doesn't require a lot of training in terms of tagging everything. So, we've seen with companies like Tesla and Waymo, they have to feed the AI neural net a bunch of data to make sure that the systems work. Am I correct in saying that this system doesn't require you to put in millions of miles of data for it to work comprehensively?
Yeah, that's exactly right. So our system doesn't require any training. There's no machine learning going on here. We're using signal processing or physics to actually measure the depth and 3D structure of everything in the field of view. And what this means is, instantly or 30 times a second, what the objects are in the world around you, how big they are, and what velocity they're traveling, without needing to know what they are. So, this is again where, you're not going to have a problem like a tractor trailer sitting perpendicularly on the freeway or overturned on the freeway, and not know there's something of immense size in front of you that you need to avoid. And as I mentioned, I think people still want to, and there's still a need to do the neural network training for other purposes, to understand it's a car or a pedestrian or a motorcyclist, for predictive engines to kind of be able to predict that the pedestrian may step into the street or that the car may swerve. You want your neural net to do those things, but you're not having to rely on your neural network to determine what this 3D structure is.
Your website states that your L4 and L5 capabilities are being limited to semi-trucks, at least I assume initially. Can you explain why you're limiting it to semi-trucks, and will we be able to see L4, L5 features in regular sedans sometime in the future?
We are not limiting it to semi-trucks. I have to go back and look at the website and see what we're saying that may cause that confusion. I apologize for that, but no. I know one of the things we do talk about is we've built some reference designs specifically for L4, L5 trucking, because they have a big focus on long range. So that's something that we've taken a specific focus on, because there is no other sensing technology that can range out to 1,000 meters. But we definitely are targeting clarity for all L4, L5, including Robo Taxi and passenger vehicles, because in the nearer distances and the shorter ranges up to a few hundred meters, as I say, we still have this benefit of seeing 3D structure and doing measured depth without any machine learning. For the longer ranges, even for things like passenger autos, that range is really powerful for doing route planning when you determine there's been an obstruction or construction zone or accident on the freeway, for example.
I've noticed that your website also states that this system has applications outside of autonomous driving. Could you touch upon some of those ways they could be used?
Yeah, our system does have a lot of applicability outside of autonomous driving, and it gets to the question you asked earlier. Do you need to do machine learning or neural network training to determine the size and distance of these objects? And we don't, because we're really domain agnostic. Again, we don't know what we're looking at. We just know the exact 3D structure of it, and its velocity and how far away it is in the scene. If you look at the scene on the screen here, and I even zoom into another point like over here, we don't have a concept that this is a stairway, but we can actually tell you what the depth and size of each stair is. So when you think about robots having to navigate a complicated factory floor, being able to determine the location and shape and dimensions of things without regard to where they are is very powerful. In a scene like this, you can even see that it would be useful for HD mapping, or you can also think of security applications. So we are really extensible because we are domain agnostic.
Obviously, the more data, the better in these applications, most people would say. Your system runs at 30 frames per second from the cameras. Is that a comfortable frames for you guys, or are you hoping in the future to squeeze out more data from higher frame rates, or is 30 FPS good enough for the system to work?
Yeah, so we think 30 FPS is absolutely fine for these systems to run at. Most LiDARs run lower than that, maybe 20 hertz or so. Aspirationally, we're engineers, so it's always about performance, right? And I think, yeah, we'll always be striving to increase the frame rate. At this point, what we're finding from the industry is that there's not a need or an ability, frankly, to handle more data. Right now, we're generating, whereas about 1.8 million points of information per frame, and at our highest rates and highest sensor, largest sensors, about 95 million points of depth information per second. That compares to the best LiDAR at about 5 million per second. So it's certainly enough for the industry needs today, but industry will be pushing the bounds of technology, the features that people want to enable, and we want to be there to support those as they come.
And finally, do you guys have a rough goal or estimate of when you want this system to be out on the road?
Yeah, so it's our goal to announce our first design wins next year, and see things in market by 2023.
Let me just squeeze a couple more in here. Do you see this as another option or the only option to achieve something like Robo Taxis? And a follow-up to that is, you don't have to answer, but do you think Tesla can get to where they want to be with their current system?
Sure. I think I will be bold or maybe provocative and say, yeah, I don't think as an industry we can ever get to true level 5 autonomous driving at large scale, meaning getting beyond the ring geofenced areas and things like that without clarity, because what's missing is a real-time understanding of the 3D structures in the field of view. Without that, we're always going to have the problem, like we looked at on the other screen, of a system seeing a drawing of a man on the back of a bus and thinking it's a real man. Or, far more dangerously, maybe somebody in a city scene is unloading a truck, so that it is a real human being that's got a pallet off the back of a truck and about to step into the street, and that person being misidentified as a picture on the back of the truck. So without clarity, you never get to large scale deployments of level 5. And in answer to the question about Tesla, obviously we feel that cameras can solve autonomous needs. That's our approach. I think Tesla's challenge, I think, is going to be, because it is a largely machine learning based system, how do they ultimately cover all the long tail edge cases that may come about? I mean, there are just millions and millions of edge cases, and when you think about how many millions of pieces of data you need to train on for each of those, it looks mathematically pretty challenging. I know they're trying to augment, or it appears they are, through using things like structure from motion, but I think even their system would be improved by incorporating something like clarity.
Thank you. Thank you so much for your time, Dave.
Oh, my pleasure. Thank you.
Yeah, so that's sorry. That's all the time we have. Dave, was there anything that we didn't touch upon that you wanted to speak on, or are you good?
I'm good, thanks. I think you guys got it.